Beautiful. All right. Hello, everyone. Welcome to the last July PyHC Telecon. The next one's already going to be in August, which seems wrong that it's almost August, but here we are. The only big reminders I have for the group are about our AGU session. We don't have a whole lot of submissions yet, and I'd love to see more from the group and from those maybe we know as a result of being in this group. I put a link in today's Telecom reminder. It'll also be in today's notes for where to go to submit to our session. And I'll probably post about it again in the Slack and poke you all as much as is humanly possible. So that's all I have for today. But the main topic that we'll be talking about is the DKISS data and Python tools info that Stuart put together for another meeting that we're going to have him talk about here as well.
Hello.
Hi, Stuart.
I've put the link to my slides in the chat if anybody wants to follow along that way. Let me see whether my screen share is actually going to work. Hey, look at that.
Woo!
No, that's the wrong. Okay, so for those of you who might not know me, I have, as well as being heavily involved in SunPy for the last too many years, 6 or so, I think, I've been working with the data center team for the DKISS, or Daniel K. Inouye's Solar Telescope. In this talk, I'm going to talk a little bit about the data that the level 1 data products that we provide and how you can get them and work with them in Python. I'm going to talk, this isn't aiming to be like a technical lesson on how to do it. I'm just going to tell you about the things that can be done and a little bit about the data and some of the more unique challenges that the DKISS data has presented. And some of the things we've done to work around those. So for those maybe more heliophysicsy people in the room who may not know too much about DKISS, it's firmly on the planet's surface and has a 4-meter mirror, actually slightly above 4 meters, but 4 meters of it's exposed to light, which if you work it out, is about 13 kilowatts of photons land on the primary mirror. So it's more than enough to boil you a kettle. And the idea is that the facility will be operational for at least 4 solar cycles, which is about 44 years. So it's going to be around for a while, hopefully. There are 2 instruments that are currently online and doing science observations, which are the visible spectropolarimeter, or VISP. Never say these out in full, and which is a scanning spectrograph. So that takes wavelength spectral data, rasters to make pictures on the solar surface, and then also has Stokes information about the polarization of the light, and VBI, which is a broadband imager, which is a very high resolution in time and space imager of the solar surface, which can be used for studying very rapid events, or used as a context imager for some of the other instruments. 3 more instruments are coming online in the next varying lengths of time, year or so maybe. For the last one, CryoNurse is pretty close to being operational at this point, I think, which is the same kind of instrument as VISP. It's a scanning spectrometer, but it's in the infrared, and it can be used to study the low corona and get magnetic field measurements, direct magnetic field measurements of the corona, which is a scientific challenge which is roughly as photon limited as studying exoplanet transits. You're looking for changes in the photon level, the level of exoplanet transits. And then DL-NIRSP, which is a IFU, so that takes 3D. It takes once it's calibrated to level 1, it captures a 3D cube of data at a single exposure. So it's space, and wavelength fiber-fed spectrograph, and VTF, which is a Fabry-Perot interferometer. So that takes narrowband images at varying wavelengths. Onto the Python tools then. So the DKIST package, which is available on PyPy and Conda, is a Python package that's been developed primarily by the DKIST Dataset Center team, which is on GitHub and is currently under review to be a SumPy affiliated package. The idea is that this library provides the fundamental tools you need to work with DKIST data in Python. It's not trying to be a general analysis library. It's just being stuff which is specific to the DKIST data. So it has a plugin for SunPy's Fido to search data sets. We'll see a bit more about that in a minute. It has helpers for downloading the FITS files using Globus, because the FITS data from DKIST is only available via Globus. And it has a dataset class, which is a subclass of NDCube, which is what you read the data into and work with it. As we'll see in a minute, we use Dask and also the GWCS library to provide coordinates for the whole data set. This plot is a VBI plot, which I have done absolutely nothing to other than throw through the default plotting and stick a grid line on it. So. Okay, so the level 1 data products are the sort of the thing that is provided by the DKIST data center. So the DKIST data center receives level 0 data from the Summit. The Summit runs some observation programs, collects some data, in some cases does some processing on it, and then overnight, when the facility isn't observing, sends gigabytes and gigabytes of data across the Pacific Ocean to Boulder, where it is cataloged by the data center and then calibrated. When we run a calibration, the output of that calibration is currently a single data set. And a data set is the very fluffy term that we use to describe like a unit of level 1 data, which is broadly a continuous set of observations taken by a single instrument at a single passband with similar instrument parameters. So it's basically what you could combine together to be a single array, which is sort of how the user tools and the DKIST package works. That means that a data set can be a wide variety of things. It can be straight up imaging. It can be intensity mode, rastering, like rastered spectrograph, or it could be a full spectroperimetric data. With Cryo, you could end up with a 6-dimensional array out of a data set. So there's plenty of data there, and there's a web interface at that URL where you can search these data sets and like download them through the web, through Globus, if you will. So let's talk a little bit more about like what's in one of these data sets. So the data set itself as a folder on your computer or in the data center is a massive collection of FITS files. So each data set can have thousands and thousands of FITS files. Currently, I checked the highest number of FITS files we have in a single data set is 33,000, but especially once the VTF is online, that number could well be in the hundreds of thousands per data set. So each, what we term to be a calibrated exposure, is put into a single FITS file. So a detector on the Summit like takes a science frame that may be a combination of many exposures, or it could be like a combination of a science frame and a lot of darks and other calibration data. But once it's gone through the calibration pipeline, you get like a single science exposure in a single FITS file, which has a complete, well-specified header with lots of information and documentation about what's in the header. But if you wanted to load the like reconstructed 5 or even 6-dimensional array of that data set, you would have to read all of those thousands of FITS files to pass the header to figure out what order those files go in and how they're organized. So what we also provide in a data set is an ASDIF file. ASDIF is a newer file format that's been developed primarily by the Space Telescope Science Institute, mainly motivated by the needs of James Webb Space Telescope. The primary reason we're using ASDIF, and the thing that like makes it different from FITS, is it has a significantly more flexible metadata specification than FITS, while also still trying to maintain some of the things that are really good about FITS, like human readable metadata. So the top of an ASDIF file is a YAML file. You can just load it in a terminal and read the top of it. And also, it's still designed to be an interchange and archive file format, unlike something like HDF5, which is like a more performance orientated or like binary file format. ASDIF is supposed to be more archivey, and like FITS as well is the same. So there's a very powerful Python library that can work with ASDIF files, and there's also some C++ libraries that will read and write, and there is some support in IDL, which I am reliably informed is them wrapping the Python library into the IDL distribution. So as I said, it's primarily built by JWST, or for JWST, so there's all of the JWST data is available in ASDIF. So what do we use? What does DKIST use the ASDIF file for? So we don't have any arrays. There's no array data in the ASDIF file. All of the array data is only in the FITS files. But what there is in the ASDIF file is literally everything else for the entire data set. So there's a table in the ASDIF file which contains every single FITS key of every single FITS header in the whole data set. And then there's also some other metadata in different formats. There's a copy of the inventory record, which is a thing that you can search for at the data center. There's a block in the ASDIF file which tells you how to reconstruct the multi-dimensional array from the set of FITS files. So that's like an ordered list of file names, and then information such as dtype and shape, everything you need to set up the array without actually loading any of the data. And then there's also a GWCS object, which has a coordinate representation for that whole reconstructed multi-dimensional array. The GWCS coordinates are never likely to be a perfect representation of everything that's in all the FITS files, but the idea is eventually they'll be really close. So with all of this metadata, like hundreds of thousands of FITS headers and potentially hundreds of thousands of files, searching for the data you want presented an interesting challenge for the data center team. We wanted to make the most powerful search interface we could that lets you filter down to the files you want based on the metadata. But also we have to maintain a web search API that is performant and easy to maintain. So what we've done is each data set has a selection of metadata that's indexed and searchable via the API. We aim to cover the vast majority of use cases you could want with that inventory record to find the data sets you're interested in. But that inventory record refers to the whole data set, all of the files in the data set. So if you search through the web portal, you'll be presented with an interface that lets you search for data sets and download whole data sets. Now, obviously, they can be quite large, but what the DKIST package allows you to do, so this is an example of searching with FIDO and finding DKIST data sets. What the DKIST package allows you to do is search for a data set, look at it and go, oh yeah, that looks like the one I want, and then to load that data set without having ever downloaded a FITS file. And then you can use the metadata representation in the asdiff file to decide if that data set is interesting to you at all, based on all the FITS headers or the coordinate information or whatever there is, whatever you're interested in. And then if you are interested in, say, some of that data set, like say in this code example here, the seeing goes really bad halfway through the data set. So we use the header key that stores the seeing, like a measure of how good the seeing is, the freed parameter, and we use that to slice the data set almost in half. So we only download the first half of the data set where the seeing is good, and we don't download the second half of the data set, which, you know, could have, in this case, I think that saves us downloading about a couple of thousand FITS files, but in a significantly larger data set, that could have saved you gigabytes of download, and also saved us gigabytes of export from the data center. So the asdiff file is designed to let you more, like, on a much more fine-grained way, work with the metadata in Python to download whatever files you want, or to make decisions, or just like do science on nothing but metadata. Like, I have a quite simple script on my computer that just downloads every single asdiff file of every single data set there is at the DKIST, and occasionally I've run script that reads them all and checks like something against every single FITS header we have, and that's like quite an efficient way of doing that. Okay, the other thing is, how on earth do you work with a few thousand or 100,000 FITS files? Because if you want to load the array, you sure as hell can't open 100,000 FITS files at once and not expect your computer to get very angry with you that you've got hundreds of thousands of file handles open. So what we do is, as I said before, you load the asdiff file and it returns you an array, this Dask array, which is the same shape and D type as the combined array, but it hasn't opened any FITS file. So that for those of you who haven't seen Dask before, this is an example of the way a Dask array represents itself in a Jupyter notebook. So we've got decompressed, we've got 75 gigabytes of array, and each file has a 20 megabyte chunk, like array chunk in it. So in this case, each chunk is a whole file, and it's a 1,000 by 2,500 array. And then there are 4,000 chunks. So that's 1,000 raster positions and 4 Stokes parameters. So you can work with this array, you can do operations on it, like slice it, you can do arithmetic operations on it, you can even rebin it using ND-cube, and it won't compute those operations until you need the array for something like plotting it, or until you explicitly call compute. And for those of you that haven't seen the Dask distributed dashboard, this is a screenshot of the Dask distributed dashboard where it's melting the CPU in my laptop, rebinning this array on my cores or whatever it's doing. So each worker on my laptop is busy doing its own section of the rebin operation, and then they're all talking to each other, and it gets to the end. And the upshot of that is I'm doing an operation on what is basically the whole data set, but, or actually in this case only Stokes I, so a quarter of the data set. And it's not opening all the files at once. It's opening, each worker is opening a file, reading the data it's interested in, doing some operations on it, and then storing a smaller amount of data in memory until it's finished. Dask can schedule locally in parallel. It can schedule over cloud workers or HPC stuff. Dask is great. Love Dask. Okay, so we're very close to the 1.0 release of the DKIST package, and we're just polishing off a few bits and improving the documentation before we do that. So the feature functionality that's implemented at the moment, I've gone over most of this, but reading asdiff files into dataset objects, searching for datasets with SunPy's Fido, various helpers for transferring files with Globus that can work with either like an endpoint on your local machine or remote endpoints. There's extensions to the ND-cube API and there's a .files attribute on the dataset class, which lets you work with the files and tell the DKIST dataset object where to look for the fits files, and then various internal functionality for building Dask arrays from those fits files. In future releases, we hope to make dataset.crop work properly. We're definitely pushing the limits of NDCube's crop API with the complexity of our WCSs, so there's some things to fix there. We want to write helpers and documentation for if you want to adjust, like modify the metadata, the WCS in particular. Various performance improvements. The fits reading isn't as fast as it could be, and some of the transforms are quite slow, and also better tools for working with VBI mosaics. That's it. If anybody has any questions or anything, I'd be happy to talk more about DKIST stuff. Jack has a question, apparently.
Yeah, go ahead, Jack.
Hi, Stuart. Thanks for the talk. Very interesting. So the ASDIF files are available right now?
Mm-hmm. Yes, all the ASDIF files are available irrespective of embargo because they only contain metadata.
Where was the link to the tools?
Too far. Where is it?
Is it DKIST DC?
DKIST.data.nsi.edu is the search bar.
No, where do I get the Python tools?
Oh, you can install it from pip or Condaforge. Well, where didn't open a new thing. Or GitHub DKIST DC/DKIST.
Okay. What I'm thinking is that we could, like, in HelioViewer, we could provide, well, maybe not images of the data, but at least where where DKIST was looking. That would also be really useful.
So not all of the ASDIF files that are available have accurate pointing information in them at the moment. The telescope's still in a sort of shared risk period where some issues are being ironed out, and so some of, especially the earlier data that was taken last year, has like pointing information that is irreparably wrong and will never be right. Some of the more recent ASDIF files have issues in them which can be resolved but haven't been yet. So
okay.
you may have mixed luck doing that, especially with VBI data. But you could do it with the VBI stuff that's available relatively well.
Okay, VBI.
Yeah.
Okay. All right. Thanks. I also second what you say about Dask. It's wonderful. Everyone should be using Dask if they're using Python.
The great thing about Dask is that it's super easy to get started with. Like the on-ramp is real friendly. You can get some benefits from using Dask with almost no added complexity to your code, and then it's only when you like really go off the deep end that it starts to get really complex.
Yeah, I've used it for coding stuff on my laptop, for speeding up stuff on my laptop, and it works there.
Oh, if you're just after the bounding box of the images, by the way, Jack, that is actually available through the REST API of the data center.
Oh, it is? Oh, even better. Yeah. Is that trustable?
It's as trustable as the information in the ASDIF file because it's made the same way.
Okay. That would be even more useful. So, okay. That's really all we're after is the bounding boxes. That would be sufficient information to tell people that at least DKIST was looking in a particular direction and at a particular time of interest.
Rebecca, I see your hands up.
Yeah, I have a question, Stuart. If someone were to learn from your method of implementing Dask, where in the code would they look?
I would maybe say that the DKIST user tools is not a particularly good bit of teaching material for how to use Dask. The way I build the arrays from the FITS files is peculiar. There's actually a project called Kachunk, which does basically the same thing as I've done in the DKIST user tools, but a bit different. So if you have a situation where you want to build Dask objects out of a massive collection of files, or especially in the cloud, or like bits of big files in the cloud, then Kachunk is designed to address that need. My long-term goal is to rewrite what I've done in the DKIST user tools to use Kachunk underneath.
Okay, thanks.
The Dask site has lots of videos and stuff. They've got lots of tools there, introductory things. I'll also make a pitch for, sorry, Will. Well, what I learned about Dask, I learned from Will Barnes. So, and he gave a talk at the SciPy meeting a couple of weeks ago, which served as a great introduction to Dask as well for some very common solar physics data processing. So, yeah, I think certainly Will's our local expert at Goddard here on Dask. I would recommend contacting him about that. Sorry, Will.
Well, was this talk
But
at
you're the best.
was this talk recorded?
That was
It
my
was
question.
recorded, but I think the recording is not online yet, but probably in like a month or so it will be online. But I'm just about to paste a link to the demo notebook I gave, which is in a repository with all of my slides as well, so you can still see.
Okay, thanks.
Yep.
Whenever you get that link to the recording, could that somehow be shared to this group? Because I'm in the
Yeah.
group.
Put it in Slack. Put it in our general.
That would be lovely.
Sure. Yep.
Thanks.
Yeah, I don't exactly know what the timeline is for uploading the talks, but
Yeah, that
they're
can be
usually pretty
famously
quick.
undependable too.
Usually the sci-fi folks are much more better about it than, you know, like typical science meetings.
Okay.
Awesome. Any other questions? Great. Thanks, Stuart.
All right, thank you.
Does anyone else have any other walk-on topics or things that they just wanted to ask about? If not, we can just wrap up early today. All right, wrapping up early it is. Oh, wait. Sorry, I just saw a message. You could. Oh, okay. So something Rebecca and I have been talking about recently is how PyHC basically can plug into the open science effort. We have the open source software tools part, obviously, but we're just thinking kind of bigger picture. What are people's ideas for open science for PyHC? If you have any thoughts right now, feel free to say them. But we can also take this to Slack or to email. So just generally putting that out there. Understandable if you don't have anything right off the top of your head, though. Cool. Well, be thinking about it. If you have any ideas, please let me know. And I'll talk to you all again in 2 weeks' time on Monday, August 7th Nick Murphy will be giving an overview of cool GitHub actions and Sphinx stuff that I set up for Plasma Pi. Procrastinate doing other things. And I love this title, so I'm excited. Cool. I'll talk to you all later.